Good morning, good afternoon, depending on where you are. This is the DOI UAS monthly user call for December. Thanks for joining us, and we'll go ahead and get started here in just about 1 minute. We'll let a few more folks filter in. I appreciate you guys joining us today. We have a good lineup of interesting things to discuss, and again, thanks for joining us. All right, we'll go ahead and get started. This is the DOI UAS user call for the month of December.
Matt, please start recording. Oh, you did. Thank you. Sorry.
Yep, all set. Thanks. I'm Matt Burgess. I'm with the USGS UAS National Project Office in Denver. We run this meeting once a month. This month we have gained quite a few new folks, so I want to welcome those folks who this is their first time, or if it's been a while since you've joined us, we appreciate having you back. We've got a good lineup of things going on this month. We'll have a talk from Mark Bauer from our office here in USGS in Denver. He's going to tell us some more about LiDAR, the latest and greatest from LiDAR. And we'll also have Brad Kekritz from the Office of Aviation Services. Brad just messaged me a short time ago indicating that he's on another call. We'll have to jump in at the end of today's. Someone muted me there. I hope you were able to hear, but Brad indicated that he's going to have to join us at the end of today's call. Typically joins us at the beginning, but we'll have to do that at the end. I'm going to turn this over to Mark, who's our month. Mark is in the National Unmanned Aircraft System Project Office in Denver. He's a data analyst and a mission operator, and he's our LiDAR expert. And with that, I'll turn it over to Mark.
Thanks, Matt. Good morning, good afternoon to everyone out there. I'm happy to be here to talk a little bit more about UAS LiDAR. First off, Matt, can you see my screen?
Yes, sir. Looking good.
Okay, good. Yeah, we wanted to give a little technology update on UAS LiDAR, kind of talk a little bit about the current market, the scanners, the trends, and then also kind of highlight some of the specifications that the vendors typically go over and report on their spec sheets. And all that stuff's pretty important because we want to be able to make scientifically defensible data. And I'll just take a quick step back for those who don't know me. Matt, he mentioned that I work at the USGS UAS Project Office, also known as NUPO, and we do have a couple LiDAR scanners here. So I will jump into our case studies and kind of show what we've got. See if this advances. There we go. So yeah, most of you guys know kind of our history. We started in 2008. I'm not going to go through it all, but I will highlight here that we did get our first UAS LiDAR scanner in 2016, and that was the Yellow Scan Surveyor Velodyne Puck that you see here on the left. And then we just recently acquired the Yellow Scan VX20. It's the Regal Minivux scanner in 2019. Just before the UAS grounding orders had taken place. We have been able to fly a little bit with that scanner under the waiver, emergency waiver process. And so we have gotten a little bit of testing and a few case studies with it. We currently have basically the M600 to fly both of these payloads. We started flying with the Vapor 55 pulse helicopter and have since switched over to the M600 for now. And then who knows what we'll have down the future once things get approved under maybe the Blue UAS drone process. So why LiDAR? Well, typically, we all kind of know that LiDAR has limitations. I was getting some feedback. Are you getting some feedback on the mic?
Yeah, I heard it too.
Oh,
I'm
yeah.
not sorry who was there. Let's see what we can do.
Okay, I think I got it better now. Yeah, so why LiDAR? Of course, LiDAR has some of its strengths and limitations when it comes to forest canopy structure mapping. On the left, because of beam divergence, we're able to penetrate forest canopy and potentially pick up bare earth for bare earth modeling. On the right side, photogrammetry, you'll need to be stationary with a number of camera movements or look angles to reconstruct a 3D model. And that typically can be an issue when you are trying to model forest structures. Those trees are moving in the wind, so any movement can cause some problems. Plus, you need a number of look angles to be able to penetrate through. So for us, we've been using LiDAR for a few different types of projects, primarily for bare earth terrain modeling and also for structure. It's also fairly common to use it, of course, for utility mapping, but for us, we primarily focus on just the bare earth and forest canopy structures. So here we've got a number of projects that we have worked on, some case studies. USGS has flown for the National Park Service for floodplain management. We've also done another National Park Service project for sea level rise and coastal change down in the Big Island of Hawaii. And then we're working on Colorado on snow water equivalent measurements and river channel sediment change for our USGS hydrologists here in Colorado. On the other side, we have worked with a BLM to do sagebrush characterization. We have a project in Colorado, downtown Denver, that looks at urban forest health. And we've done some 3-depth forest validation with URAS data center using both ground-based LiDAR systems and comparing it to airborne manned flights for the 3-depth program. So it kind of gives us that look between all the various data collects, and being able to add in UAS LiDAR to help validate the studies has been pretty important. So I'm going to switch gears and just kind of highlight the types of UAS LiDAR out there. You can really break it down in between 2 different types in non-scanning LiDAR. And on the left here, we've got mechanical scanners, and on the right, we've got non-mechanical scanners within this category. What we typically hear most common and what's really been dominating the market is the motorized optomechanical scanners. These particularly collect in spinning rotational mirror type setups. So all these different types that we have here is really how it goes about and collects and covers an area. So with a rotational mirror, we've got this particular setup. With beam scanners, what you get here is a very small movement or a prism or a mirror that is readjusting to focus that array so that it's collecting an area. And then moving over to non-mechanical scanners, we usually have a array type setup where we're having individual laser scanners put together in a pattern to cover that area. And then over a non-scanning flash LiDAR, you can think of flash LiDAR as actually being kind of like a camera flash, where the picture was being taken by a flash of light. It covers a broad area, and instead of individual points, it will collect and feed back that particular return. These various 3 scanner types are fairly innovative, and they're primarily being driven by the autonomous automobile industry. I haven't seen too many of these scanners available for the UAS market yet, with the exception of this particular one here, the red tail. We'll cover that a little bit more. What I want to focus on a bit more is the motorized optomechanical scanners. We'll talk about this market and kind of what's available. They do have their strengths and limitations. These scanners really come with high performance, but they do cost a bit more. A number of these guys, since they're fairly new technology, have kind of limitations in manufacturing at the moment. So we're still seeing advancements, so we'll see where that goes in the near future. So switching gears to motorized optomechanical scanners, what are they composed of? Typically, I like to think of it as two systems. If you were to go out and purchase one, you can go out and buy just the scanner itself, and that's going to consist of a semiconductor laser diode, also the motors and the optics for that rotational mirror. You're going to get a photo detector, and you're going to see the beam, this red beam here, go out. That's the out turn, and then the reflected echo come back in and be received by a photodetector itself. So this is, you can buy these particular scanners, they're inexpensive per se, but when you really need to put it on a UAS, you need a whole integrated solution, a payload that has been developed so that you have a standalone power supply, a recording device, some sort of SD card or hard drive that's been integrated in. And the most important thing here is a GNSS or an IMU, both of those setups. Sometimes it's referred to an INS, an inertial navigation systems, but that's going to allow us to determine where our points are so we can georeference those returns. Traditional LiDAR systems are electromechanical. They do rely on these moving parts. And now for the most part, they are dominated by the UAS market at this time. So I did make a list of current scanners, and I've been updating this list as we move through the years. This particular, what I'd like to highlight here is the left side is the actual scanner itself, and the right side here is the integrated solution. And I've shown a bunch of these examples from a few different companies here that do take those scanners and integrate them into a standalone payload. I've labeled or ordered these by price from bottom up. And also, as you see, as you go up the list, we have a laser range and accuracy and precision. They get better as we go higher up. So I've been noticing that there's been refreshes from manufacturers. We get typically, like the Velodyne Puck came out in 2014. We've seen updates in 2016. The Regal Minivux, for example, has just come out with 2 new refreshes. And primarily for that system, they're just updating the rotational speeds and also point densities. Everything else has been pretty much the same with the Regal Minivox system. So if you look over here at some of the specifications, I do list the ranges for each one of these scanners. As we go up the chain here, you'll see that starts to increase. And I've kind of colorized these blue because we have field tested that or have gotten that information from trusted sources that basically have been using them out in the field. The ones that are labeled in red here are strictly from vendor specifications, which typically mean that they were measured in lab conditions. So once you get out in the field with an integrated solution, you really start to see the sweet spot for mapping when you start to test and use ground control points and get that complete package out in the field. You'll know where that sweet spot is. And we'll talk a bit more about some of the specifications on why that is coming up. I will also wanted to note that as you go up in the list, you typically gain more in the returns. So the capability of these scanners goes up a bit more. You know, we have dual returns down here. We typically can get about 5 returns with the Regal Minivox. And these scanners are a little bit heavier for small UAS, but they start to go up as well in terms of range and number of returns. One other thing that I wanted to mention is that the range on these scanners should also include your slant range. And I'll talk a bit more about that as well. So there are a number of different integrators out there. I just listed a few here. You can see that most of these scanners are either the Velodyne Puck, a Quanergy system like you see here on the GeoQ, or like a Regal Minivox. And these vendors will typically offer their own products. They will also offer their own software packages for data processing, and there's a ton of options out there. I counted up to about 26 vendors as of October. I know that number has grown since then. I've actually found a few new manufacturers as well. Just to highlight, Regal is also an integrator and a manufacturer, right? They will make the scanner, providing. So not every manufacturer does this. For example, the Velodyne puck that you would see over here, you typically have to go find, either do it yourself or find an integrator to merge that together to have a payload for a UAS applications. Let's see. So I wanted to highlight a bit more about some of these other scanners that are out there. You're going to see a whole bunch of options. There are some very specific designs tailored for various needs. The Regal MiniVox 1DL is primarily designed for corridor mapping and utility surveys. LiDAR does have the ability to pick up power lines, and that's been beneficial for the mapping community, because structure for motion does struggle a bit for those very thin lines when you try to build a 3D surface. So that's one option out there for folks. I've seen this underground LiDAR mapping unit called the Hover Map that actually rotates 360. And this particular scanner rotates 360 and itself rotates 360, so you can use for underground mapping applications. Again, we talked a little bit about the MEMS LiDAR. That's a new technology that's coming out. This Redtail RTL 400 is a newer UAS payload. I have not been able to look at it in depth yet. There are some flash LiDAR solutions coming out, also some phased array options. These particular array setups are still being really driven by the autonomous automobile industry. I haven't seen many options yet for UAS. Coming over here, I do have a few other motorized optomechanical scanners. I haven't had a chance to really fit them in the list. This IBO Lux system is an older scanner that's since been replaced by this Livux scanner because it's been reduced into weight and size. It's fairly new, and I've noticed that it comes with a spiraling flower type pattern that collects a very interesting pattern so that you can get closer, but also it's lighter in weight, so you can fit this particular system on a DJI M300. It's the first one that I've seen that will really fit on a smaller UAS. So if we change the wavelength, we can get into green-blue wavelength scanners. So at 532 nanometers, we can start to do shallow water surveying. USGS doesn't own any of these particular scanners, but what's out at the market now, I found these three. The Astrolite Edge, which is actually developed here at a company of Boulder, Colorado. We had gotten some test data from them. We flew a section over the Blue River in Colorado, and it did return this kind of example of results where you can penetrate the water surface and get bathy collects. If you look over here, they have done a refresh with this particular scanner. They are now, at first you had to fly fairly low. It was kind of scary and dicey. You were off of the water surface by about 3 meters. They've since increased that to about 20 meters, which makes it a bit easier for the operator or the remote pilot to collect. The depth penetration for all these scanners is about the same at 1.5 secchi depths. Haven't really been able to test more, but that is for very clear water. It is very difficult because of these challenges to penetrate the water surface. There's a lot of absorption, water refraction that happens with the bending of light, and you can't just increase your laser power. You've got eye safety regulations, and you can potentially burn out the diodes. So it is a challenging technology. So for the most part, it's been focused kind of as a niche, basically just in shallow water, clear water types. There was one other thing here I wanted to mention, that this particular scanner, the Astrolight Edge, to note, the swaths are very small. They're about 3 meters, whereas in these Regal scanners, they're fairly accurate, but swaths were not listed here because they are profilers. So it's a very thin swath. You're only getting a few centimeters of a collect with those particular scanners. So again, this Astrolite's the one that I've seen that has the most at this period of time. Hopefully there will be more options out there soon. So another thing I want to switch gears is people ask me how I process the LiDAR data, what software do we use, and it is really going to depend on what particular scanner that you purchase. So we've went with the YellowScan system, and it does come with their own proprietary software. You can use also, say, Regal's software package as well to read that file, but I wanted to highlight here, this is the stuff on the left that we go out into the field and we collect. So these are the various files that we will pick up with those scanners, and I will import those into either a Cloud Station or a Trimble POSPAC UAV. Since we are using a Trimble IMU, we get a license from them so that we can read that trajectory. So basically that IMU is like a flying rover per se. It's out there, it's collecting a trajectory, and eventually we're going to want to correct that. So we basically input a Rhinex file from our base station so we can do what is called a GNSS inertial processing correction. What's nice about this software package is it goes out and it downloads all the ephemeris information, the satellite constellations that were observed during this base station collect. So that is done all behind the scenes for you, so that when it applies that mathematical correction, it looks at those constellations and it has the data needed to reposition a new line for you. That new line is going to be more accurate, and we will save that out as a text file. And that text file is typically called an SBET, Smooth Best Estimate Trajectory. We will then import that back in the Cloud Station so that we'll have a better georeferencing fit or position for our point cloud. So in this software package, we can primarily focus on the transects themselves, cut off the turns. We keep each one of these lines that we want. There's a lot of other garbage, of course, in the flight, so we'll remove that by filtering the process there. And we can also then filter down our scan angles, and we can add in our ground control points as a text file to help position this further and define it into a proper positioning that will line up with our RTK surveys. There's a few other inputs that we'll use here. We definitely want to keep our lever arm angles. So that's basically our offset from our GPS antenna, and that is measured so that those offsets are compensated and get applied, those corrections within the Trimble POSPAC program. We also want to put in our base station reference frame projection so it knows what we all collected in. And we also have our bore sight angles, which are typically measured, at least YellowScan for us goes out and does those. The manufacturer provides what the bore sight angle corrections are. And what does that mean? Well, really, bore sight angles are there's a distance and offset between actually the center of the laser scanner and where the IMU position is. So there's an offset there, and these bore sight angles will help correct for that positioning so that we'll get a better, more accurate point cloud. Once we process this out, we will get a raw LAS file or a PPK corrected LAS file if we go through these steps. An individual LAS file for each one of these transects. I'll then import those into another program like Cloud Compare. You can use whatever you have access to, merge those points together, and then we can colorize and we end up with a final PPK LAS file or export out a compressed LAZ file. It's the general workflow there, and it can vary depending on what units you have in hand. So again, the products we can colorize our point clouds based off of height or height above ground. We can point classify our point clouds. We can actually code our buildings right. We can then also go code our high vegetation, low vegetation to create a bare earth model. If we generate or fly structure from motion, a photogrammetric collect, we can colorize with RGBs colors. I typically use Global Mapper software to do all these products, but you can also use ArcGIS, LP360, TerraSolid. There's a number of programs out there. So I'm going to switch gears and talk a little bit more and dive into these technical specifications. We'll run through these if we got time. I have a number of case studies to show, but each one of these specs is important because it can affect how your data is collected and the accuracy and the precision of the data. So if we're trying to measure forest structural properties like canopy height, canopy cover, or leaf area index, you know, how do these things that the various vendors list on your scanner affect those particular properties? So we're going to go through this a little bit and highlight some of the important ones. So the first one is multiple returns. Of course, we highlighted this a bit at the start. Multiple returns are essential for bare earth modeling. And we can typically see, because of beam divergence, we can pick up various returns of the tree where our last return is ground, but it may not always be ground. Our last return might end up being part of the tree, for an example. Well, there's a couple different ways that this is actually recorded. There's two types. There's discrete and waveform, and it primarily between these two types, it's how the data is digitized between them. So the discrete form is going to digitize these returns here off of the top of these peaks and just record that information of the peaks. The waveform is actually going to digitize and collect all the values along these waves, so that is recorded within the file. So just something to note, because when you start to read about different scanners, you're going to want to know if it's a full waveform type of system. Here's a case study that we did on the Denver Federal Center. This is just structure from motion. What you're looking at here is a 10-centimeter cross section across these two trees. And you can see we got some of the tops of the surface of the trees themselves. But if you come down here and look, you know, the forest canopy has, you know, basically prevented us from drawing across the line here, right? Collecting the full bare earth model. With the LiDAR system, the Yellow Scan Surveyor, we have multiple returns. First return is the blue. Second return that it's capable of is the red. You can see we have coverage below the tree canopy here. We also flew with the Yellow Scan VX20. It has less points, but they're a bit more accurate and precise. And what I did see with this particular scanner, because we can fly higher as well with it, that's another benefit about the Regal Minivox, is we were able to pick up, say, some of the tree stem here as well. We also have up to about 3 returns. These yellow points is the third return that is penetrating through the forest canopy here. So a lot of folks say, well, why don't you just interpolate the structure from motion? Well, I kind of wanted to highlight this little square here. If we zoom in, you're going to see this is the structure from motion underneath the forest canopy. You can kind of see this noise that was collected. If we interpolate between this noise, we're going to get this kind of up and down surface, which really isn't going to model underneath the forest canopy very well. So that's primarily why we'd like to use the Surveyor and or the VX system. Any of the LiDAR systems that can penetrate the canopy is going to get us a much more accurate measurement of those areas. Here's the VX20 in the same spot. And again, this is a 3D view of the same area that kind of shows the tree shadows that were collected under structure from motion. Yellow Scan Surveyor in the same area, and the Yellow Scan VX20. We can minimize some of these tree shadows with flying perpendicular, so doing two transects that go across, and we do that with the VX20 often. Because of the yellow scan surveyor, we have to fly a bit lower with this one, and we typically get many more points with this scanner. What I wanted to highlight a bit more about how flight heights really affect your dual returns or your multiple returns. So this particular test was flown in Granby, Colorado. This is over an Aspen stand. And on the left here, we flew at 30 meters. And you can see we had a 30% increase of multiple returns when we flew at that flight height. The vendor says you can fly a lot higher, so we would go to this max range of 45, but I noticed a significant decrease of points of second returns. So you'll get less points below on the Flores 4. So it's something that you want to consider when you do your mission planning. Your flight height will drastically affect your number of returns. So switching gears from multiple returns, we're going to talk a little bit about scan angle and slant range and how that really affects your mission planning. So you want to consider your slant range. When you look at this diagram here, really, we just broke it down. The vendors will typically give you what your field of view is. So we divide that in half to get our scan angle. We also can set our nadir range, our flight height, and know what this is. So with just some basic trigonometry, we can go out and calculate what our slant range is. And I did that here for R2 scanners. And so these various setups, if we were to go fly at 30 meters and actually increase our scan angle to 60 degrees, we are well within our slant range here of what the vendor says we can typically hit. So at 51 meters. And I did the same sort of thing here for the Regal Minivux, and this really just helps us understand how to properly mission plan so that we can compensate for some of this terrain and to really get good, accurate results from our points that are hitting off on this high slant range. And why is that important? It's primarily because of beam divergence and how it affects our off nadir accuracy. So if you look here, we'll have a spot size on the ground. At nadir, it's going to have this kind of shape. But off at 45 degree, we're going to have an elongated axis here that can be measured. So the vendors typically like to define this beam divergence in milliradians. And here I listed the milliradians for the Regal Vox system, the Minivox, and the Velodyne 16, which is the same as the HDL Velodyne 32. So the Minivox is a 1.6 milliradians beam divergence, and we can calculate based off of our flight height what that will be. So 16 centimeters will be in a nadir position, but if we were to look at what we were going to be at 45 degrees, we're typically going to enlarge this to 22.6 centimeters. It's a bit larger. You'll also notice the Velodyne puck is even larger than that, 30 centimeters, and it goes up to 42. So the larger the spot size on the ground, the more uncertainty you'll have in your measurement. So we typically like to limit our scan angles. We are like recommending that we will do no more than plus or minus 45 degrees due to the spot elongation. So there are trade-offs with that, and I'll show a case study here. But before we jump into that, I just wanted to mention that those spots, ideally, we like to kind of show as a circle, but really they're a small rectangle pattern that you get from these scanners. And the vendor will give you horizontal and vertical dimensions of these scanners. On the right here, you can actually use an infrared camera and see what the spot looks like. So this is for the VLP Velodyne puck, the 16 laser spot. And you can see the spots here hitting on a wall with basically using an infrared camera. And we can measure what our heights will be, what that spot size will really be instead of a circle. So 9.3 centimeters at 4.6. We typically fly at 31 meters with this scanner. And I usually fly the Regal Minivux at 61, so our size here is 9.8 and 3. So what's interesting is those are about the same size based off of those two flight heights. We can fly higher with this system. I got the specs from the vendor for the Quanergy. We don't have this scanner, but I noted quickly that that scanner has a much longer, kind of a long and skinny rectangular pattern, 21 centimeters in the horizontal and only 3 in the vertical. So something to note. One of the case studies for why this is important with the scan angle is that here we flew this particular project with 60 or plus or minus 75 degrees from nadir, and those are colorized here in red, and the blue points are just points within plus or minus 45 degrees. So you can see we reduce a lot of the scanner noise here. This is an area of low grasses. The juniper tree here, you can see the blue points dropped off significantly in this little section. So there is a trade-off. You know, if we're not slinging shots out at high scan angles, we may not hit this tree to build that structure. So we may have to compensate and actually fly a perpendicular pass or tighten our transects, do more passes over to get that area collected. This just kind of shows again the flight planning for those two different types of scan angle collects. The red is the plus or minus 75, and the blue is plus or minus 45 here. So we're going to cut off a lot of points, and we're going to spend more time out in the field if we're going to reduce our scan angles. And then also another important aspect to consider when you're looking at these LiDAR units is intensity, which is of course the measure of return strength of the laser pulse. So different objects are going to have different intensity values. For example, water absorbs the return fairly often, and you don't get any point. In some situations where you have concrete surfaces, you're going to get a very bright reflect. So these scanners will record these in different bit ranges. The Velodyne Puck does an 8-bit intensity from 0 to 255. Whereas 255 is typically the high-end reflectance, and 0 is no reflectance. And then the Regal Minivux is a bit more, has the capability of capturing 16 full bit. And why this is really important is if you were going to put ground targets out that were reflectors, you can use these to define you can use the intensity to define your reflector locations. So I've got examples here on the right side that shows a reflector point and how the 16-bit is a bit more defined, where I can see that intensity pop back for that target. Whereas with the Velodyne Puck, it's a little bit noisier. It's harder to see some features. So that's something to consider when you are looking at various LiDAR applications for UAS. Point density comparison. I got this from Lewis Graham at GOQ. We weren't flying power lines because we're not typically looking at it, but at the time I didn't have the Regal Minivux, but it was just nice to compare. So you can see here, of course, your flight height is going to be a major factor of your point density. You're going to see your scanner speed vary as well. So there's a number of factors there. So scanning rates are another big one. We'll breeze through this. Pulse repetition rate here, you're typically going to see from the vendor of how many pulses you get. Well, what's really important is what's usable within that 90-degree swath, so just keep that in mind. We can set the rotational speeds on the Regal Minivux, but for this Velodyne Puck, it's fixed that the vendor, the integrator, can fix based off of the final integration. So we can get various speeds with these as well. These scanning rates are important because it's how it affects scan patterns. So when you see these patterns here, the in-track spacing is a function of the vehicle velocity and scan speed. And the cross-track, this direction here, is going to be a function of the repetition rate step size. So as the pulse vapor here was moving forward, you can see there's a slant pattern as well. It's typically the faster you move with the UAS, the more slant you're going to get. Due to the forward motion of the scanner. And also some of these gaps that you see here is due to the drone pitching. So the pulse vapor was notorious for kind of rocking and pitching back and forth, and you'd get these gaps in there. We didn't really have that problem with the M600. It's fairly straightforward, but this isn't really an apples-to-apples comparison because we have the VX and the Velodyne puck on both sides, but you can kind of see how smooth this one laser is. Also note that this has 16 lasers. This one has 1. When you have one single laser, it makes it much easier to calibrate that particular system. Calibrating 16 lasers isn't typically done. This scanner was designed for the autonomous automobile industry, so they allow a bit more noise within their point cloud because it doesn't need to be as precise or accurate. Just a quick refresher. We want this, right? Accuracy and precision to be good. If we have poor accuracy and poor precision, we can have some problems. What I wanted to highlight here is if you have poor precision, we have noise and spread within our point cloud, and we can measure that noise in our point clouds, and this is using LP360, and what we've got here is a hard planar surface that we've measured. This was actually done by GeoCube, but we've started doing this ourselves. We can look at various objects and see what our spread and measurements are. So what we're reporting here is at 1 sigma, so basically 68% of the time, our points are going to fall within a spread of 1.6 centimeters for the Regal Minivox. The Velodyne puck is 3.5. It's a bit more noisier, but we are going to get outliers outside of that 68%. And you can measure those, and what we've got here is a range. So this range is a peak-to-peak range of points from top to bottom that you could potentially measure up to 12.5 centimeters and 24 centimeters for the Velodyne puck. So they are a bit noisy still. However, a lot of that can be minimized by when you use binning methods to develop, or I should say to produce, a raster or DTM file. We can either pick a minimum binning option, an average, or an upper, so that it's going to draw that line across the board there. So that's, the reported noise or precision that we get with the VX and the Velodyne puck. Accuracy can be affected by a number of variables. So anytime you have a measurement, you can introduce error. So I just wanted to highlight what I did here is break this down to 4 different groups. Over here, range accuracy. So this is really, we can have error introduced because of our pulse or the beam divergence or the shape of the pulse. So, and the accuracy of the timing instrument. These are all important. The vendor typically reports this in millimeters of how good it's done, and it's measured in the lab. So another thing that can affect our accuracy is how accurate this spinning rotation device is. How consistent is it? So the resolution of that instrument. Moving forward over here with the IMU itself, we can have errors within our IMU, our position, our velocity. Like I mentioned earlier, this creates a trajectory, and so that trajectory could be off a little bit. Post-pack UAV, the software package that I use to produce those corrections, does report these errors back to down to usually 2 to 4 centimeters, say with the Regal, or I should say with the Aplantix 15 or the Aplantix 20 IMUs. So these are something to consider as well. You can get error that creeps in this way. And of course, we can have error within our GNSS reference base station. Opus typically reports back those errors, and this can be a function of a number of different sources. It can be anything from atmospheric effects or satellite clocks or even a surveyor just not setting it up properly or using a wrong height on their antennas. So your network accuracy cannot be any better than this. So it's really tricky when a vendor tells you how accurate your LiDAR scanner is. Well, you really want to look at all 4 of these functions because error will compound, and as you add that in, you'll end up will have you can get down to 3 or 4 centimeters, but you can easily have error up to 10 or 12 centimeters with these various scanners. And it can be because a number of these things crept in error on your measurements. Hopefully that makes sense. A few more quick little case studies that I'll breeze through here. I know I'm running short on time, but we've got a point here. This is a comparison between the VX20, and we also have the structure from motion point cloud in the brown line here. These green lines are the VX20. We used one GCP point, and it lined up fairly well. Without using this GCP point, you can see a shift here of a few centimeters that was off. And this is our transect line here over some vegetation. I played around with a GCP point or 2 points or all of the points. And basically what I've got here is, here's our point. This was using with GCPs. This was without using GCPs and or using just one. So yeah, we pretty much determined we'd like to use ground control if we can to refine our model. It does help. It's probably going to be your best bet to getting your points to align up. I do like collecting structure from motion because it is another way to validate my data. I have another line here that I can see that compares and matches and lines up with my LiDAR point cloud. And we typically collect our structure from motion point clouds with using a separate ground control set of points. We like to use the arrow points and maybe set up a separate base station. Typically we have to set up a base station for our LiDAR, but if we keep those two separate and we can line those up, we can validate our data. These last few little examples are just some structure from motion again with collects with the surveyor. This is a cottonwood tree. It kind of showed limitations of the point cloud. We didn't get the top of the point cloud at all because of the number of look angles. Again, a structure here, because the UAS typically flies, reduced transects, we're not spending a lot of time scanning the complete building structure. But here you can see the dark lines, kind of the structure from motion rounds things out a bit more. We can fix that by collecting more photos, right? But when we fly UAS, we don't often have the time to collect photos around those areas, and it might not be something that we're very interested in. With the LiDAR, it does hit some of the sidewalls a little bit better. You can see it did not get under the porch with this particular collect, but just something to consider. For us, what's really important is the kind of grassy surfaces. You can see the structure from motion highlights the top of the points here, the surface. The LiDAR with this particular Velodyne puck has a big distribution of tall grasses. And we like to do like the binning method using the minimum average so that we'll collect and average the ground surface and reduce basically the grasses on top. So that is what is our final measurement. So to really summarize here, we're always learning. We're tweaking our best practices as we move forward with these scanners, and we often have different requirements for our projects. We can tweak those project setups with our mission plans based off of what our final product is. So if we're focused on bare earth terrain, we can set up our scans in one way. If we're more focused on forest canopy, we can then tweak our mission planning so that we're able to collect. So it's nice to have that acquisition control, so that can be useful for a number of our projects. The other thing I wanted to highlight is vendor specifications are often measured in lab conditions, and they don't really consider all the variables, so be careful there. Are basically, if you don't, and one of the things I wanted to mention, if you don't really need dual returns at all, you can probably just get away with structure from motion. Photogrammetry is an awesome technique to be able to go out and measure a 3D surface. But just to understand your strengths and limitations, that's important because we kind of want to be able to develop scientifically defensible data. We like to collect both structure from motion and LiDAR just so that we can help validate our point clouds, our data sets. It's also important when you come back and report your data and you want to define in your metadata to say, how did you validate? What did you do to do that process? The last thing here is more validation for us is required. We'd like to continue to test different ground control targets. We haven't had the opportunity to do further in-depth studies yet, so we're hopeful once the grounding is lifted that we can continue to move forward with that and see what works best with these various project types of acquisitions. So with that said, I can take some questions, or we'll turn it over to you, Matt. And thank you very much.
Great, thank you, Mark. That's excellent stuff. We have a series of great questions in the chat, and we'll be able to get to a couple of those. I want to just remind the folks who are on the call. Brad Kekritz is standing by. He's about to give us a brief as well. So if you're waiting for Brad, it'll be just another minute. Thank you, Mark. Joe Adams from our office has been able to field some of the questions in the chat, but
hey, Mark, I would like you to answer one question from Eric at Glacier National Park. Eric asks, would you increase your scan angle in steep mountainous terrain, or is the increase in scan angle only necessary for small landscape features on otherwise low angle or flat terrain?
Yes, so the answer to that is yes, I would, because we'd be more perpendicular to that surface. So we're really going to introduce more error. Our accuracy is going to go off a bit more when we have that high scan angle because of that elongation of the spot size. But if there are, say, surfaces in high, like cliff faces, for example, then what I would prefer is to basically, we can go higher scan angles because we're not going to have as much error introduced because of the stretch there, right? It's how we're collecting. So I don't know, hopefully that answers the question.
Excellent. Yeah, I think so. Joe, did you have one other question from the chat that you think Mark could answer here, and then we'll move forward?
I think I've answered most of them, Matt. So please, anyone speak up if you have a question that has not been answered in the chat.
Great. Thanks so much, Joe. Yeah, there's great stuff here. And I think Mark can attest, he could go 3 or 4 of these 1-hour sessions for LiDAR. There's so much to it. Also want to thank our speaker this month, Mark Bauer, for presenting a lot of information on LiDAR, technology that's evolving quickly for UAS, and certainly look forward to another update sometime in the future. Once again, thank you for taking the time to join us this month. We appreciate it, especially folks who are new to this call. We appreciate you taking time out of your schedule to join us. This meeting occurs the first Wednesday of every month, and we're always looking for speakers. So if you've got something that you'd like to share, something that worked well, something that didn't work well, if you have a topic that you'd like to share with the group, go ahead and shoot me an email, Matt Burgess, and I'll get you worked into our schedule here. Again, thanks so much for everyone taking the time to join us. Apologize this month for all the email traffic and the calendar hoopla, but I think we've gotten through those hoops, and hopefully if you can't join us from a computer, a telephone option might be something that works for you. With that, I will go ahead, just refer you to your agenda. I made a bunch of possible things that may be of interest for UAS interests. Again, there's a bunch of links on there. Feel free to send me things that you think might be worth sharing with the group. Again, I appreciate your time, and hope everyone has a happy holiday season, and we look forward to seeing everyone first of the new year. Thanks again, everyone, and take care.